Okay, we are starting Unit 7. This is gases and organic chem. So a lot of gases is reviewed from sophomore year, but let's talk about the basic principles of gases. The first is that gases have mass. Whether the gas is buoyant or not, like as in whether it floats or not, it does have mass. This can be proven by simply taking a tank, empty, and then filling it with gas and weighing it before and after. Right? Clearly, as you fill the gas, it will increase in mass, or fill the tank, it will increase with mass, and you know that it has mass. Point 2, it's easy to compress gases. Because gas particles are far apart from each other, there's lots of space in between. So we can demonstrate this with a simple piston, where if you push down on the piston, you're forcing the gas particles close to each other. That's why it's compressible, because there's so much room in between, right? So due to the amount of space in between. Gases expand to fill their container. So whatever container you use to hold a gas, that's the volume the gas will have. All right, I can take a mole of gas and put it in a container this big, or I can take a mole of gas and put it in a container this big, right? Like let's say this is 1 liter and let's say this is 10 liters. So by describing the amount of gas with volume is actually not a very good way to do that. Right? Just because you say, oh, I'll sell you this 10-liter tank of helium gas, even though it's only got 1 mole in there, right? You're not getting any more helium than if you bought the 1-liter tank filled with 1 mole. Make sense? The best way to describe how much of a gas you have is through moles, not by volume, because gases will continuously expand. Gases can mix or diffuse easily, right? And the reason why is because of this same reason. It's lots of space in between the particles. So if a perfume mixes with another perfume, it's because there's nothing stopping the two particles from moving into each other's space. Right? So if there's a spill, somebody spills some perfume at like Macy's or something, all the particles float outward, but then some lady walks by who's, wearing a very pungent perfume, the two will mix, and that's why it's like deathly smelly in the perfume section of Macy's, if you've ever walked through there. Yeah. Nick.
Polarities have an effect.
What's that?
Polarities have an effect on the diffusion of gases.
Polarities?
Yeah.
Not really. No, once they're independent and already vaporized, then polarity doesn't play a role. Polarity does play a role in how easily something vaporizes, though, right? But once it's airborne, it's airborne. Gases exert pressure, and this is probably the key point here. We need to talk about pressure, what causes it. So first of all, pressure is force divided by area, all right, technically speaking. Now, we are not talking about pressure of individual points. We are talking about pressure of a gas. And so the cause of gas pressure is collisions. Particle collisions is what causes pressure. So whenever you have a problem or question involving pressure, the main thing you should be focusing on is what causes the amount of collisions. How will the amount of collisions change? If I do this, what will that do to the amount of collisions? If I do this, right? So all gas pressure we're going to be referring to is predicated on collisions. And we'll get into more detail here in a second, but if there was one takeaway from this first section here, this is the important one. Gas pressure varies with temperature. We will talk about that. There's specifically a law for that. And gases, despite their differences in chemical properties, they will all obey the same physical laws, meaning we use all gas laws for all gases. regardless of formula or composition. Okay, so those are the general principles. Let's move into measurements. So gases need to be measured on an absolute scale. And an absolute scale is one that has no negative temperatures. Because much of how we describe gases is going to be calculated, we cannot be entering negative values into our calculations. The formulas that we have are predicated on there being a total scale with no negative values. That is why we have the Kelvin temperature scale. All right, so first thing you do always in any gas problem where you are provided a temperature is you must convert the temperature to Kelvin. All right, that should be the first thing you would do as soon as you see a temperature. Now, the temperature to convert to Kelvin, it's simple. It's just Celsius plus 273. Right? So we just took the temperature in the room here. We said it was 23 degrees Celsius. So 23 degrees converted to Celsius plus 23 plus 273, so 296 Kelvin in this room. Okay? That is the point of a Kelvin scale, so that you have a zero, an absolute 0 point. Absolute 0 is equal to 0 degrees Kelvin. It's the coldest theoretical temperature that can exist. And the definition of absolute 0 is there is no atomic motion, not even vibration. Hence theoretical, because if this has never been measured, because in order for it to be measured, you would need some kind of operational temperature probe, but nothing mechanical will work when there's an absence of atomic motion. So it's kind of like a paradox. Does that make sense? Like your thermometer can't work if nothing can move, right? Okay, so let's talk about the atmosphere now. I'm going to add a page so I can better illustrate this. So before we talk about that barometer, let's talk about the Earth. So here's the surface of the Earth. The Earth has an atmosphere. Here's air. And wherever you are on the surface of the Earth, there is air above you. Air, like everything surrounding the Earth, is being affected by the pull of gravity. So particles are always being pulled downward by gravity. Now, if you are standing here, then the column of air above you is being pulled downward onto you by gravity. That amounts to what we know as pressure, specifically atmospheric pressure. Now, there's a standard pressure. The standard pressure is at what's called sea level, and it's 1 atmosphere. So whenever I say standard pressure, I'm referring to 1 atmosphere, sea level. We here in Chicago, we're basically pretty close to 1 atmosphere, right? But if you were to move somewhere, like over the summer, I went to Colorado Springs. We had friends. They live in, higher up because Denver is known as the Mile High City. So when we were there, the column of air that was above us over there was shorter. So with less air above you, there's less force being pulled downward on you, right? The air is being pulled down with less, there's less air, so there's less pressure, right? So lower pressure, less air, affected by gravity. Because the outer limit of the atmosphere does not change, right? You go up in the atmosphere, then the amount of air, there's just going to be less air above you. It's not like the air increases above you because you go up on a mountain. All right. So are you guys okay with the concept of atmospheric pressure and how the pressure that's observed will vary based on your elevation? All right. This would also work if you went into like a really deep pit, but there's no pit that's a mile deep. Like yes, mountains can be high, but it's not like you have the equivalent of a ditch, which would be really kind of scary actually, because that'd be a lot of pressure. All right, so back to the barometer. A barometer measures atmospheric pressure, and the way that it works is that the air pressure pushes down on a liquid mercury, and inside the barometer, so inside the cylinder here, you have a vacuum. Remember, a vacuum means absence of matter. So no gas, no air. If there's no air inside the vacuum, that means there's also no pressure inside. No pressure in here. So because there's no pressure, and because fluids are not compressible, the air pressure can push down on here and force it up the cylinder. And however high it goes in the cylinder is a measurement of that atmospheric pressure for the day. So these are typically measured in millimeters of mercury. So if we took the pressure with a barometer here, we would see approximately 760 millimeters of mercury. And that is where the equivalency comes from 1 atmosphere. 1 atmosphere is equal to 760 millimeters of mercury. And that's how we can convert back and forth between units. 1 atmosphere pressure, 760. It's also equivalent to these other units. Pascals are a commonly used pressure unit as well. Kilopascals, kPa, is this divided by 1,000. So 101.325 kPa is equal to 1 atmosphere. Torr. A torr is named after Torricelli, who was the first person to make pressure measurements. 760, it's basically 1 torr is equal to 1 millimeter of mercury. And PSI is an engineering unit, so pounds per square inch. These are all equivalent to one another. So basically, whatever pressure unit you are given in a problem, you need to convert them ultimately to atmospheres because it needs to be used as atmospheres in our gas laws. Right? Atmosphere, the important one. Okay. So, example, your bike tire says 22.5 psi. Right? What is this in atmospheres? Well, it's just dimensional analysis. There's 14.7 psi per atmosphere. So we're looking at about 1.54 atmospheres in the bike tire. Okay, simple conversion. All right. In lab, when chemical reactions take place, if we need to collect that gas, then we're going to be using what's called a manometer. So a manometer is an apparatus where a reaction takes place in here. It produces a gas, and the gas flows, and into a tube on one end, there is a liquid, originally mercury, and the other end is open to the air. So what we have then is two forces battling each other. We have the air pressure pushing down here, and we have the pressure caused by the gas that was made pushing here. Now, in this specific scenario, because the pressure of the liquid mercury is being pushed on the left side more, that means the pressure that's produced is greater than the known air pressure. Because that's known, and because the tube is graduated, meaning with markings, the difference in height between the two sides, here and here, we can use that difference to determine the pressure of the trapped gas. Because the pressure, well, of the gas, which is this guy, is equal to the known atmospheric pressure plus the pressure difference from the two sides, which we can measure by the height difference. So first of all, if you see a diagram like this, the first thing that you should notice is which side is pushing harder, the left or the right. the gas or the atmosphere. That's the first thing you should decide. In this case, it's trapped gas, which is pushing harder, so the trapped gas pressure will have a greater value. This value, which is known, to this value, you add the difference, because that's how you're going to get a value that's greater than this. So, example. Let's do this example right here, because it's right in front of us. The difference in height, so this difference right here, (32.6 millimeters is the difference in height. Okay, so the air pressure is known in atmospheres. I'm just going to give it a value. We'll say 1.02 atmospheres. So I need to translate this into atmospheres so that I can actually add them together, because you can't add units if they're not the same. So 760 millimeters per atmosphere. So we're looking at 0.0429 atmospheres is equivalent to the difference in height. So the pressure of the gas would be 1.02 plus 0.0429. Roughly 1.06. And conversely, if the level of mercury on the gas side were higher, that means that the air pressure is lower, and instead of adding, we'd be subtracting, because the pressure of the trapped gas would be less than the pressure of air. Okay? So you'll see it both ways. Anyways, that's how we use a manometer. And once we know the pressure inside, then we can use that value for other calculations. So let's just do one more example of that. So all right, take a second. Let's find the pressure of the gas in atmospheres. Obviously, you need to convert these units ultimately to atmospheres. What do we get for a value, guys? Yep. Which makes sense because your air pressure here is pushing harder than the trapped gas. So this value is going to be a greater value than this value. Now, to compare them, they need to be both in the same atmospheres. So in this case, the difference in height is going to be subtracted from the air pressure, because this value that you're trying to get is a lower value because it's not as strong. Okay. So gas laws. There are some gas laws, most of these that we've talked about before, so we'll kind of breeze through these. So the first gas law is Boyle's law. Boyle's law was originally stated as this, right? The product of the pressure and the volume is constant. Now this, of course, is assuming that other variables that are not mentioned are constant. So we're assuming moles is the same, temperature is the same. So if the pressure increases, the volume must decrease. That's what this tells us. So by realizing that whatever combination of pressure times volume is going to be constant, then that allows us to state P1 times V1, which is equal to K, is also equal to a different pressure times a different volume combination. And eventually we can just root out the constant and write it in its simplified form. P1 V1 equals P2 V2, Boyle's law. You can only use this again if the other variables are constant. So you would have to know that. Pressure and volume are inversely related. Okay, so what that looks like then on a graph, inversely, as the volume goes up, the pressure goes down. Charles' law. Volume and temperature are directly proportional. So V over T, the ratio of volume to temperature, and of course temperature in Kelvin, this only works if you're using the absolute scale. V over T is constant. As temperature goes up, volume goes up by the same proportions, which similarly then leads us to the commonly used version of Charles' law, V1 over T1 equals V2 over T2. Gay-Lussac's law, pressure and temperature, right? Similar relationship. The ratio of pressure to temperature is constant, which brings us to this simple law, P1 over T1 equals P2 V2, or P2 over T2. Avogadro's law is not one that we mentioned when you guys were sophomores, but it works by the same principles. The volume of a gas is proportional to the amount of the gas in moles. So through similar extension, assuming that your pressure and your temperature are constant, this can be observed. Okay, we've already talked about Avogadro's number, but this relationship is what led us to figure out what that number was. The fact that 12 grams of carbon-12 is equivalent to that number of atoms. All of these laws together can be combined to arrive at the main gas law that you'll be using 90% of the time, the ideal gas law. The ideal gas law incorporates all of the variables, and it's unit specific, meaning that whatever pressure value you have given to you in a problem needs to be converted into atmospheres. Volume must be in liters, and temperature must be in Kelvin. Right? This is stuff that you already know. If all of those gas laws were rearranged and set equal to K, then eventually we can derive R as equal to PV over NT. And the value for R, like I said, is unit specific. 1 mole of a gas takes up 22.4 liters at standard temperature, so 273, we should mention, is standard temperature. 1 atmosphere, standard pressure. This is what's known as STP. So whenever we say STP, those are the values you should be using. We then can calculate the value of R, which is known as the universal gas constant, 0.0821, and the units are liters, atmospheres per mole Kelvin. That's why this is unit specific, because you're going to end up canceling these units, but in order to do so, you have to have these values in these units. So, let's try one out. We've got a 2-liter flask. That's clearly volume. And we have a pressure of 885 millimeters, a temperature of 0 degrees. How many moles are in the flask? So they're asking for moles. That means we're going to be rearranging to solve for N. But you need to make sure that you've converted everything properly. So 885 millimeters, to convert that to atmospheres, we're going to have to divide that by 760. Zero degrees Celsius in Kelvin is going to be 273 Kelvin. So we have the volume. So pressure, 1.16 atmospheres, 2.0 liters. The gas constant, and the temperature. I know it's drag to write units in all of our calculations, but this is kind of a silly thing to lose a point on the AP exam if you don't show your units for R and show the cancellations taking place. All right, so atmosphere is in the numerator, atmosphere in the denominator. Liters, liters. Kelvin cancels Kelvin in the denominator, and the only unit you're left with is 1 over moles, which of course is 1 times the reciprocal, moles over 1, which is moles. Hence, the unit's going to be moles. So that means we set this up correctly. Let's go ahead and calculate. So we're looking at about 0.104 moles of helium gas. In the second question, how many moles are present under similar circumstances? And they ask how many grams is that? Okay, so we're going to carry out an ideal gas law calculation again, but we're going to take it one more step and convert the moles to grams. So first, solve for moles. PV over RT is equal to N. 2 liters, volume is given. This is going to be 298 Kelvin, and the pressure is given. So 3.5 atmospheres, 2 liters, 0.0821. So 0.286 moles of chlorine. They wanted it in mass. So a mole of chlorine, 253.8 grams. So we're looking at about 72.6. Okay. Ideal gas law, plug and chug. All right. Make sure you have the right units. What is the pressure exerted? 15 moles, 50 liters. Okay, we don't need to do it. This is just another example of using ideal gas law. So let's skip ahead. Let's talk about variance. While the ideal gas law is great for solving things like pressure, moles, temperature, whatever, we need to find other things. And so if PV, which equals nRT, so PV over RT is equal to N. We also know N is equal to molar mass, or grams divided by molar mass, sorry, right? This is how we have described it before. The College Board uses capital italicized M for molar mass, right? As if we don't have enough M's in formulas like molarity, so capitalized italicized M. So N is equal to G over slanted capital M. The point is, we can substitute this in for this. In doing so, PV is equal to GRT over slanted capital M. And this will allow us to solve for molar mass. And the units of molar mass, of course, grams per mole. So, what is the molar mass of the compound given this information? All right, so let's see what we have here. Let's plug everything in. We need to convert 710 torr to atmospheres. So this will be 0.934 atmospheres. 100 Celsius is 373 Kelvin. And when you're given density, 0.977 grams per liter, you are given two values. You are given the mass and you are given the volume. The volume is implied, it's 1. So if we plug everything in, grams, 0.977 grams. And did not plan my spacing very well. R, I'm going to write R, don't have enough room. Temperature, 373 Kelvin. Pressure, 0.934 atmospheres. And the volume, like I said, because the density right here, grams per liter, the value for the liters is just 1. So the molar mass is going to be 32 grams per mole. Okay. So if you need to find the molar mass of a compound that is in gas form, this is how you would do it. I'm going to skip the empirical formula part. I'm just going to jump down to the density. So we can also determine density from the ideal gas law, because if density is mass over volume, mass is measured in grams, volume is measured in liters. So if I took PV is equal to GRT over M, and I rearrange this such that I get P times molar mass is equal to GRT and divided by volume, and then I can leave these here and divide out the RT, I get pressure times molar mass over RT is equal to G over V, aka density. So we can solve for density. 273 or 27 degrees Celsius plus 273. So what are we? That's 300 K. 735 millimeters. 0.967 atmospheres. Okay, so 0.967 ATM times, this is oxygen, so the molar mass is known. It's 32.0 grams per mole. R and T. We get 1.25 grams per liter. As far as how we arrived at those units, let's track them. So, atmospheres in the numerator, atmospheres in the denominator. Moles in the denominator of the numerator, moles in the denominator of the denominator. Kelvins, the only thing you're left with, grams per liter. Okay. I don't think we need to do another example of that. Let's talk about the combined gas law here, and then we'll be done with this section. Okay, so the combined gas law combines all of the little laws we talked about earlier, right? The Boyle's law, the Charles law, the Gay-Lussac law, the Avogadro's law, right? It combines them all and sets them equal to a constant, which sets them equal to each other, and that we arrive then at this. Now, notice that moles are conserved, and if moles are constant, that means moles drops out. So this is actually the equation we will use whenever your conditions change. If you have a situation where either the pressure, temperature, or volume changes, or multiples of those change, you can plug them into the combined gas law. Now, the thing about this is more useful than individual gas laws because let's say we have a situation where the temperature is held constant. If the temperature is constant, just scratch out the temperature, and that means you're really dealing with Boyle's law. Right? If the volume is constant, then you scratch that out, and now you have Gay-Lussac's law. So this is the most versatile besides the ideal gas law because of that. So the hardest part about a problem like this is tracking what's the initial, what's the final. So you have to read these kind of problems carefully. Sometimes you need to read them more than once. So we have a gas in the cylinder, and we have a volume, and we have a temperature, and we have a pressure. Okay, so this is stated pretty straightforward. This is V1, this is T1, this is P1. The gas is compressed to a new volume, so this is going to be V2. The temperature is raised, so this is going to be T2. And what's the new pressure? So P2 is what's being asked. Okay, so just take your equation and rearrange it to solve for P2 before you do any substitutions. So V2 will go down here. T2 will go up here. Now, as far as units, notice the combined gas law does not have the universal gas constant. R is not used, and R is what was unit specific. So if R is not here, your volume does not have to be in liters, your pressure does not have to be in atmospheres. You can just leave them as is. But the one thing must always be converted as what? Temperature must always be in Kelvin, right? So 30 Celsius, right? So 30 plus 273, so 303 Kelvin, and then 820 plus 273. $10.93. So that's really the only conversion we have to do. Okay, so the original pressure, 710 torr. The original volume, 500 milliliters. Oh, actually, that's annoying. It's 2 sig figs, so 5. 5.0 times 10 to the second. Our new volume, 25 milliliters. And our new temperature, our original temperature, 303 Kelvin. Okay. Kelvins, volume. This is going to be in torr. $51,223. We'll just have to call it 51,000 torr. That's going to be our new pressure. Now, is this reasonable? What are we doing to this gas? You're starting at a volume of around 500 milliliters, and you are compressing it down to 25 milliliters. So you're basically bringing it down to 1/20th of its volume. The gas particles are a lot closer to each other, right? Okay. What does that do to the number of collisions? Should increase it, right? Because the gas particles now have a shorter distance to go before they collide with the wall because they're in such a smaller space. What do we do to the temperature? We raise the temperature, right? So by raising the temperature, the gas particles are moving a lot faster. If they move a lot faster, they will have more frequent collisions. So we do expect a dramatic jump in pressure, which is what we see here. Okay. And that's good enough for now.